So let's work through this example problem. I guess the first thing that we should do is figure out what we know and what's going on. So, all right, so important things. The merry-go-round starts from rest. Rest is always an important thing. It undergoes a constant acceleration of 1/25 radians per second to get up to full speed. If it rotates 8 radians, that also seems important, while it is speeding up, how long does it take? That's one of the things we're trying to answer. And if it has a radius of 4 meters, what is the tangent speed of a point on the merry-go-round's outer edge? So that's another thing we're trying to answer. Okay, so here's the information we've got. Let's collect it all in one place. So stuff we know, that is, it starts from rest, and it's a merry-go-round, so it's rotating. So that means that's going to be our omega naught is 0. It undergoes a constant acceleration, so that's alpha. And it rotates 8 radians, so that's theta, but it looks like it's a change in theta because that's how far it's rotated. So 8 radians there. And we want t. How long does it take? And then later on, we also were told it has a radius of 4 meters. And what's the tangent speed of a point on the merry-go-round's outer edge? So let's draw a picture. We're not told which way it's accelerating, so let's just assume that it's accelerating so that it'll be spinning like this. And the tangent speed of a point on the merry-go-round's outer edge, so like right there, that's going to be then sort of the speed on a tangent line. So that's actually going to be a linear speed. So that's going to be something like that. That's the thing we want to know. And we're told the radius. It's 4 meters. We also want the tangent. Okay, so how can we do this problem? Well, these are the things we know. We also know that this is constant, this acceleration, so that means we can use a constant angular acceleration problem. And given the things we know, I think that this one looks like a good candidate. The final angle is the initial angle plus the initial angular speed times time plus 1/2 the acceleration times time squared. You might say this looks an awful lot like this guy here. A constant linear acceleration equation. And you would be right. We got final position, initial velocity times time plus 1/2 the acceleration times time squared. So that's the math we're going to be doing. The math for angular stuff that's rotating, is pretty much exactly the same as the math for stuff that's just traveling along in a straight line. Okay, so that's the equation we've got. Now let's go ahead and rearrange it so we're solving for the variable we want. So I'm going to subtract the initial angle from this side, and then we got omega t squared plus 1/2 alpha t squared. Sorry, that should just be t. So this is my delta omega. That's something I've got. Sorry, this is my delta theta. That's something I've got. Omega naught, that's my initial angular speed. So that is equal to 0, which means this whole term cancels. And then I have acceleration. So now I can go ahead and solve for t. Let's just rewrite it here. And I'll multiply both sides of the equation by 2, cancel this 1/2. Divide both sides by alpha, cancel the alpha, and I will have 2, my change in theta over my alpha, t squared, so I'll take a square root of both sides, and there we go, I've solved for t. Okay, so now let's plug in the things that we know. Delta theta is 8 radians. So 2 times 8 radians. Alpha is 1 over 25 radians per second squared. All of that is square rooted, so just subbed in the things that I know. The radians will cancel because we're multiplying and dividing by those. And we'll have 2 times 8, and then dividing by 1 over 25 is the same as multiplying by 25. Same thing with dividing by 1 over seconds, or radians over second squared. That's the same as multiplying by second squared. And then let's see, 2 times 8 times 25, that's actually 400 seconds squared. Still take the square root, and that's a square root I can actually just do in my head. That tells me that time is 20 seconds. So that's the answer to my first problem. Time is 20 seconds. Now let's figure out the tangent speed. Well, all right, that's going to be the speed that a point on the edge is going in linear variables. So this, we're looking for something in meters per second. So I guess in order to answer this, we're actually going to need the final angular speed, because it wants to know when it's up to speed. So that's the end, after it's accelerated. All right, so we're going to need to solve for something else. We'll need omega final. And I would say let's go ahead and just use this equation. It's another constant angular acceleration equation. It's just the final speed equals the initial speed plus the acceleration times time. You know all of the variables on this side. That guy is equal to 0. The angular acceleration is 1 over 25 times radians per second squared, and time we just solved for, it's 20 seconds. So one of the seconds cancels, we're left with just radians over seconds. That's the correct unit for omega, and then we got 20 over 25, which is the same as 4 over 5, which is the same as 0.8 radians per second. So that's its final angular speed. If we want the tangential speed, well, we're going to have to multiply that by the radius. Because if you want a tangential speed, remember, this is the relationship. It's omega cross product with r. And r is going to be this vector from the middle out to the point that we're interested in. Here it's the outer edge, so it's the full radius of the merry-go-round. Now what's the direction of omega? Well, assuming it spins like this, we can curl our fingers with the spin, and our thumb will point in the direction of omega. So if it's rotating like this, omega will point upwards. So let's just write that off as an aside here. If it rotates like this, the final omega is up, out of page. And we can write that with this symbol. So a little circle and a dot in the middle of it. That means omega is pointing up towards you. Of course, nothing in the problem told us that omega was going this way. We were just given magnitudes, not directions. So I suppose it's possible that instead the merry-go-round goes the other way, like this. And if that was the case, well, then we take our right hand again, and we're going to now curl our fingers with the motion like this, and our thumb's pointing down now, so into the page. So if it's rotating like this, the omega final is down into the page. So perpendicular to what I can draw here, but we do have a little symbol, this X in a circle. That's how we draw a vector that goes into the page. So I can't actually, draw the arrow on the page. So in either case, it's either coming up out of the page like this or going down into the page like that. And either of those vectors are perpendicular to r. So when we go ahead and do the magnitude, because we want the speed, we don't have to actually worry about the direction, that's equal to the magnitude of the final speed times the magnitude of the distance from the center of rotation, the middle, out to whatever point we're interested in. Here it's on the edge, so again, that's the full radius, times the sine of the angle in between them. And I guess I better use a different symbol for angle, so I'll use that one. And we'll just denote this is the angle between the vector omega f and the vector r. So here, that's 90 degrees, because the vector r points from the middle to where the tangent point is, and omega either points straight up out of the page or straight down into the page. So in either case, that's 90, and the sine of 90 is just 1. So this is going to be the magnitude of the final angular velocity times the magnitude of the distance from the center to the point we're interested in. Here, that's the radius of the full merry-go-round, times sine of 90 degrees, because these two vectors are perpendicular to each other. And we can just plug in what we know. So the magnitude of the final angular velocity is 0.8 radians per second. The magnitude, the distance from the center to the point we're interested in, is 4 meters. And the sine of 90 degrees is just 1. All right, so 0.8 times 4, that is 3.2. And now we got to talk about units. So the units of velocity is meters per second, but we got these radians still hanging around if we just kind of like look at what we've got going on with units. And radians are kind of the magical disappearing unit. And they reappear again, if we were to divide out, if we instead had the tangent velocity and we divided by the radians to get the angular velocity, the radians would just reappear when we divided out that meters, which seems very upsetting. But what's actually going on is the radius, you can think of it, it's 4 meters, but it is a radius. So it's 4 meters per the radius of these things. So that's kind of the radians. So if that makes you feel better, you can add in a radians here, and then they'll cancel just as they should. But you got to be careful, because angular stuff always has like this phantom radian unit kind of running around and popping up. So if the meters show up, you can make the units of radians, you can just think of them as disappearing. If you divide out the meters and you have just 1/2, well, the radians will reappear, because all of the angular variables are things like radians or radians over second squared, or this, it's 0, but its units are radians per second. So just be aware that there's weirdness going on with the units here. But in any case, we have now solved for the other thing that we are interested in, the tangent speed of a point on the outer edge of the merry-go-round. And that is how you would do any of these sorts of angular acceleration problems, particularly when the acceleration is constant. So we can use our constant acceleration equations and do all the math just like we would if we were doing just a linear constant acceleration problem.